I want to introduce Ron and Sergio, our guest speakers for today. Ron is a certified consulting meteorologist and an ASHRAE fellow with over 40 years of experience using state-of-the-art research findings and wind tunnel modeling to find creative solutions for air quality problems. Ron is currently the president of Petersen Research and Consulting. Sergio is an environmental engineer with over 18 years of experience in air quality. Sergio's expertise in research, regulations, and consulting gives him a unique insight into the interaction of the theoretical and practical aspects of air quality. And with that, I will go ahead and turn it over to Ron to get us started.
Good afternoon, everyone, and welcome. Sergio and I are going to talk about the development and implementation of a new alpha building downwash option in AERMOD. I'll start out, and then we'll be kind of tag teaming throughout the presentation here. What we're going to cover first, some new building downwash enhancements, the genesis of PRIME2 and ORD, Office of Research and Development Enhancements, the PRIME2 alpha version development, and we'll get into the definitions of what alpha versions mean and how they fit into the regulatory environment. And then these new model evaluations, and then we'll talk about some plume rise enhancements to PRIME and evaluating those, and then what's next with EPA and model improvements with building downwash. So the building, just an overview of the building downwash enhancements that we're going to kind of be talking about. PRIME2 is really a new building wake theory based on industry-funded research with Air and Waste Management Association review and oversight. And it was put into, this alpha option was put into AERMOD 19191. In case you don't know, you can run this right now. The ORD enhancements also are in AERMOD 191, and they new cavity and wind speed theory based on research carried out by EPA. And then plume rise enhancement, an API-funded study. We're trying to improve the plume rise predictions in AERMOD, and that will likely be included in the next AERMOD release, which would be next year. So now we'll kind of go into the detail of these enhancements, how we got there, and I believe Sergio is going to pick it up from here.
Yes, thank you, Ron. So the genesis of PRIME2 was based on the need for a new model for downwash. I think with the 1 hour standards, we realized that there were many more complicated problems now with passing evaluations. So then one of the big problems that had been neglected for a long time was building downwash. So in 2016, we presented some of our findings at the 11th EPA Modeling Conference and also at the Specialty Conference of 2016. And then we decided to form a subcommittee under the Atmospheric Modeling and Meteorology Committee. This is under the Air and Waste Management Association. And we had two goals in mind. I mean, we didn't only want to fix downwash, but we also wanted to make sure that other improvements in the model, new science could be implemented a little bit more clearly and with more transparency. So the first goal for the PRIME2 subcommittee was to establish a mechanism to review, approve, and implement new science into the model. And this for this and future improvements. So for example, there were some updates that EPA would do before 2016, and EPA would just implement them indiscriminately, right? They did some analysis themselves, they did their own evaluations, and then they put them out there. Then the user community would do more evaluations and actually find that there were things that perhaps weren't ready to be default options. And then on the other hand, if there was any research that came from outside EPA, there was a long process. It took, I think, 3-4 years before, for example, the ARM2 options were implemented on a case-by-case basis in AERMOD. So we wanted to expedite that process and make it a little bit more transparent and efficient. And then obviously the second part of the equation is we wanted to provide a technical review for improvements to building downwash in AERMOD. And like Ron mentioned, we obtained funding in 2016 and 2017 from the Electric Power Research Institute, the American Petroleum Institute, the American Forest and Paper Association, and the Corn Refiners Association. So with that money, we were able to actually carry out some research. It had been many, many years since like research had been done in building downwash. So we needed to update a lot of the science, a lot of the equations, a lot of the assumptions made there. And there on the right side, you can see that we have the wind tunnel that was used, and we have one building, and we have different surface roughness. And in the middle, we have a little bit of some space where we would have the probe do some measurements. And I think that's on the next slide. So we did velocity deficit measurements, upwind of the building, basically like the wind flow undisturbed, and then downwind of the building to see at different distances what was the effect of the different structures. And along with velocity deficit, we also looked at the turbulence intensity. So we used an Omni probe, like you can see there on the picture, and we tried to see, well, what is the how is the plume interacting with the specific structure as you get to different locations downwind from the source. So in 2016, we went to the EPA Regional, State, and Local Modelers Workshop, and we presented some of the initial results from this work that was done. And then there was a journal article published in the Journal of Air and Waste on August of 2017. That first article was basically documenting all the problems that we saw with building downwash. So we thought that the first step is always to find what is the problem so that we can address those issues. So obviously there are a lot of still pending issues. So we've been trying to prioritize those that are most relevant as it comes to agreement with the databases that are available. And then in 2017, something really important happened. EPA released their white papers. And the white papers was the first time that we get a glimpse into what EPA was thinking, what their priorities were, where they were focusing some of their efforts. So as we were working with EPA, like before, like EPA was working separately from everybody else, and they were very protective of their model. So we came to them and we told them that we needed to collaborate. And obviously they had the final say on what goes into the model and what becomes default, but they don't have the they don't have the ability to do all the updates that are necessary. So this was the first positive effect that happened from this collaboration, where EPA actually says, okay, these are the white papers, these are the areas that we're interested in, and EPA is doing some research themselves, and they're also allowing for other research like the PRIME2 research to be used for that as well. And they did reference there in that white paper, like the journal article that we wrote in 2017. And then obviously, like we parameterized all that in some equations, like the velocity deficit, the turbulence intensity for the different structures, and we submitted it to the Journal of Wind Engineering and Industrial Aerodynamics. And the point here is that we wanted to make sure that any type of proposal that we had to EPA was technically valid and justifiable. So we submitted it to peer review. It got published as it's shown here, and again, that's the basis of the new theory that is inside what is now the alpha options of PRIME2. And these are some of the enhancements that we found with PRIME2. This is again like new research, like something that wasn't known before, but the building wake effects decay rapidly to ambient levels above the top of the building. This is something important, given that sometimes a very tall stack was still subject to significant downwash effects that does not correlate with what we saw in the wind tunnel or what we would expect in the real world. And then another finding that we had is that the lateral turbulence enhancement in the wake is actually less than the vertical turbulence enhancement. So currently in PRIME, they're assumed to be equal, but once you do the actual testing, we realize that those are not the same. So we parameterized that as well. And then we also evaluated approach turbulence and wind speed at a more appropriate height. And we evaluated streamlined structures as well. Obviously, when you have a sharp edges on a building, is different than if you have like a round tank or some kind of streamlined structure. So we parameterized that as well. And then we also looked at wake effects. They would decrease with roughness increases. So basically, if you have more roughness around your site, the effects from building downwash are decreased. And then along with that, the other interesting thing that happened is that EPA was doing their own type of updates and their own research as well. Just give me 1 second here. I think someone was joining, so let me accept. Okay. So the first issue was there was a mismatch between going from the cavity region to the re-entrained plume, re-emitted plume, which is shown on the top right. And if you ever plotted this, like you would see that the cavity region, once you got out of it, there was a little dip, and then it kind of went back up. So that was a discontinuity that ORD identified and corrected. The second update was the effective wind speed. Currently, PRIME uses the stack height for the wind speed, and obviously the wind speed is very important as it comes to calculating concentrations. But then on this second update from ORD, they're actually using the average of the height of the plume and the receptor height. So that's kind of like that is the U effective, the wind speed that is used for that calculation. And then the third update was the vertical turbulence intensity. Jeff Wheel had it at 0.7, but somehow when the model was implemented, there must have been a typo and it was 0.6. So that was one of the updates they made. And then on February 28th of 2018, there was a Downwash summit. And we spent the whole day with EPA, Office of Research and Development. Obviously, Ron was there, I was there. And also, we had some members from the APM committee. And we sat down with Office of Air Quality and Planning Standards. We sat down with Office of Research and Development. And we basically presented the research that we had collected. And this was extremely beneficial because that was the first time that we were all in the same room looking at the same thing. And EPA OEQPS confirmed that the updates could be included as an alpha option in future releases. And they told us that it would take about 3 to 4 months. And I think for the most part, it was in the ballpark. And one of the things that they requested is that we put each one of the updates as a separate switch so that they could be turned on and off, so that they could evaluate kind of like a combination of switches and try to figure out which is the best, the one that gives the best performance. And then they also told us that for it to go into a beta version, and I'll explain that in the next slide, we had to go through the requirements of section 3.2.2 of alternative modeling. So basically, this is this is one of the probably more substantial results from this engagement with EPA, that there was an implementation process that was established. So in that implementation process, there were improvements submitted to EPA. In this case, some of them came from ORD, and some of them came also from CPP, like what we call the PRIME2 updates. And then those would be released as an alpha option. And the alpha option is a new concept that EPA released, where this is an option that is purely for research purposes. So this is for the community, the user community, to explore and use these options and provide feedback as it comes to how they perform. And then once you meet the requirements, which are the 5 requirements I have here of section 3.2.2, then you can go into the next step, which is the beta option, which is an option that could be used for regulatory purposes on a case-by-case basis. And a lot of these items have already been addressed. We have the scientific peer review because we submitted our journal article to peer review to a journal. And it's applicable to the problem. In this case, it's building downwash. So we've met we've met actually all of these requirements. But we're still going through the process of trying to evaluate whether there are other updates or refinements that need to be made. But after you go to the beta option, then you have to go through notice of proposed rulemaking before you can make an option be default. So that's the ultimate goal. We want to evaluate the options that we have, figure out which ones work best. EPA, which my understanding right now, they're looking at the combination of different options, and Ron's going to talk about some of the latest updates that have been done on building downwash. And then based on those updates, there might be a beta option that is released in the next AERMOD version that comes out. So anyway, so that was a big highlight of what happened through this interaction. On May of 2018, Ron and EPA also met and looked into the alpha options. So there was an ongoing discussion, an ongoing collaboration. We looked at all the options that could be available, turning them on and off. And And then on October 2018, the PRIME2 code was established so that it could have switches to turn on and off all the options, not only the ones that were done by the PRIME2 subcommittee, but also the ones that were done by ORD. March 2016, there was a bug that was identified by EPA, agreed to fix it. There was more research that was needed, and I guess maybe I should stop here for a second. Like, once you get into the model, you fix one thing, and somehow that incorrect assumption was balancing the model to give you good performance. So once you fix one part of the model, something else gets out of whack, out of balance. So as that's one of the things we realized, and that was what got us into looking at Plume streamlined equations and also platform structures. So it is an ongoing process, these refinements and this evaluation, but as we correct one thing, we figure out that there are other things that also need to be corrected as well. And then Office of Research and Development, they continue to work on elongated buildings and updated BPIP. And then on August 21st of last year, AERMOD 19191 was released, and that was the first time that the PRIME2 options were, and also the ORD options were available to the user community. So the switches are here, like it's AWMA U effective. They changed the name we had, it was Prime U effective for us, but basically this defines the height used to compute the effective parameters. And now they're all calculated at a height of 30 meters. Then we have AWMA U-turb, which enables the calculation of turbulence and wind speed. And that's basically the new formulation that was released. And then we have the AWMA streamlined. So this is a new set of constants for structures that are streamlined, like tanks, like hyperbole, like any type of structure that it doesn't have sharp edges. And then the ORD updates are the ORD U effective. As I mentioned, it's using a different height for wind speed to calculate concentrations. ORD turbulence, which adjusts the vertical turbulence intensity to match what Jeff Wheel intended in his paper. The ORD cavity that fixes that discontinuity between the cavity region and the re-emitted plume. And if you don't apply in the switch, I guess the current AERMOD is applied in that sequence. So in summary, from the start of the research to get in the PRIME2 to code, it took about 13 months. And getting to implement the PRIME2 alpha option took about 10 months once the code was provided to EPA. So EPA was working as hard as they could, but obviously they have many other requirements and many other things that take their time. But we thought that the interaction with EPA was extremely useful, and that this has paved the way for new improvements to be implemented also to the model. So now I guess we'll talk about some of the field observations. This is where we actually have the rubber meet the road, where we actually see how these new updates actually look when you implement them and you compare them with field observations. So I'll turn it over to you, Ron, at this point.
Okay, thanks, Sergio. The first thing we'll do is kind of look at the databases that we used. Some will probably be familiar to you. They're Bowline Point along the Hudson River Valley. You can see the stacks and the buildings, a fairly typical power plant. And then the next data set was the Alaska North Slope, fairly short stack, 2 buildings, well, quite a few buildings, but BPIP just picked up those 2 main buildings. So that's one issue with this study is, the building dimension inputs. And then it's the grid was put around the facility. So it's a little different. It's not one receptor for a year. It's a measurement grid downwind. The next study is actually a fairly new study, PRCI, Bulco, Oklahoma, which was about a year-long field study, and they put out the monitors at these various locations. Monitors one was kind of far field, 2 is kind of very close, and I can't probably use a mouse or see the mouse, but the stack, you can see where the stack is. It's called the C9 stack, and the buildings. And then we have the 3 receptors, 1, 2, and 3. and 4, and then there was a Met tower right there down by Receptor 4. So the next slide shows kind of the buildings, if you want to show that one. And the primary stack was you can see it's shorter in the buildings. That's called the C9 stack. And that's pretty much the main stack that was operating during the study. There were a few other stacks operating intermittently, but most of the time that was the primary stack. And that shows you the source parameters for that stack. The next slide, yeah. The emission rate was fairly steady, 15 grams per second. Short stack, 11 meters roughly, very hot plume, high exit velocity. The other stacks intermittently ran and were included in the evaluation. Okay, next slide. So as we go through the evaluation, in case you're not familiar with some of the statistical parameters, the robust highest concentration represents a smooth estimate of the highest concentration based on an exponential fit to the top 25 concentrations. So you sort your data from high to low and take the top 25. A QQ plot, they're generated by sorting the data, observed, predicted, from high to low, and then just plotting them, observed versus predicted. So they're not paired in space and time, but it's kind of the typical way EPA presents the comparisons. And that's kind of what we're going to look at now in the next few slides. The model runs, just to give you an idea, P2 stands for the 191 PRIME2 version, which uses the new Plume height wind speed for concentration calculations, a new wake formulation, and it also includes that ORD cavity fix. That's really the official PRIME2 option. ORD is just the ORD improvements we talked about, and P just stands for this current AERMOD with prime as unmodified. So now let's take a look at the results for like Bowline point. Now each slide will be kind of the same. On the upper left, you're going to see the QQ plot. On the bottom, we're going to see the robust highest concentrations, and then maybe a picture of the site where you can see the power plant and receptors 1 and 3. So for this study, you can kind of see that PRIME2 performs pretty good, and it predicts on the high side, whereas Prime is actually showing maybe the under predicting in the high numbers. And you can see if you look at the robust high concentration ratio predicted to observed, Prime is under predicting about a 0.83, PRIME2 1.28. So I'd say that they're actually performing about the same, but PRIME2 is tending to over predict, and the ORD version is over predicting even more. Let's go to the next slide.
Yeah, Ron, I don't know if you want to mention about the biased and unbiased model, you know, like the dotted lines.
The dotted lines are really a factor of 2. Is that what you're talking about? Yeah. The dashed lines there are the factor of 2 agreement. The solid line represents 1-to-1 agreement. Now on the Alaska North Slope, you can kind of see the receptors were kind of scattered all over, and it was kind of every day was a different field trial. So it's a little different data set than a data set where you have hourly observations at one receptor for like a year. So in this case, you can see the purple line is the AERMOD, which actually agrees quite well. ORD over-predicting, PRIME2 over-predicting significantly. Where you can see the ratio of predicted to observe in the bottom table is a factor of 3 for PRIME2, factor of 1.5 for ORD, and Prime is right on the money, really. So that's an interesting observation that we noted that we wondered why PRIME2 was over predicting, and that led us, as you'll see later, to some Plume rise research, Plume rise prediction research. It may be that Plume rise is being underestimated. Now for the PRCI monitors, we have monitor 1, which is kind of far field, almost out of the building wake effects. And I think you can see that really the curves on the QQ plot are fairly close together. but they're tending to underpredict in the high end. But PRIME2, if you want to move the cursor there, Sergio, PRIME2 shows a 0.86 agreement, very good. And ORD and PRIME tend to underpredict more and more. This is something we're going to see at most of these receptors. Receptor 2 is close in, about 140 meters away, going to be higher building downwash effects. But again, the monitors are, or the models are underpredicting. PRIME2, a factor of 0.6, ORD 0.4, PRIME about 0.4. So significant underpredictions at that monitor also. Next slide. Yeah, there you go. That's monitor 3. Again, building downwash effects should be fairly significant here. And the building input should be fairly straightforward. In this case, it's just straight toward the monitor, not at an angle. And here you can see that PRIME2 is almost getting right on the money, 0.97. Really good agreement. ORD 1.55, overprediction, PRIME 1.34. So this is the only monitor where the models are overpredicting. Monitor 4, again, building downwash effects a little further away, but a corner, kind of at a corner. PRIME2 is almost right on the money, 0.97. ORD underpredicting, and PRIME is underpredicting. So the next one kind of is a summary table of the performance. And if you look at it, you can see that PRIME2 really is kind of overall performing better than PRIME or ORD, with that Alaska kind of being an outlier. It's kind of a different data set. PRIME is doing really well there, and we're doing a factor of 3 over prediction, but it's kind of a little different type of data set. And if you want to use consistent data sets where you have monitors for a year, we're showing that PRIME2 is showing the overall best agreement. Next slide. So this kind of led us to some questions about the Alaska database. Why is it over predicting so high? And we wanted to look at the Plume rise model in PRIME. It's really a new numerical solution of the basic equations for conservation of mass, energy, and momentum. To solve those equations, you need 2 entrainment constants, alpha and beta, and those are important. We'll come back to those in a minute. The Plume rise model really accounts for temperature stratification, wind shear, streamlined descent, the enhanced dilution in the building turbulence, velocity deficit in the wake. So it's a really pretty good model. It's similar to models developed by other researchers who tested their model against field observation, but came up with different entrainment constants. So next slide. Reasons for this study was that PRIME2 was showing a tendency to overpredict for a little bit for Bowline Point and quite a bit for Alaska. So this could be due to the Plume rise. Maybe it's underestimating the Plume rise. So what we did is we did a study that was for API. We wanted to look at the entrainment constants, alpha and beta, and to determine if different constants would give you better Plume rise. So we had a study funded by, the next slide there, I think shows, well, he didn't say, but this study was really funded by the American Petroleum Institute. And we looked at 2 Plume rise databases, one EPA database, I won't go into the details, and one a CPP wind tunnel database where we had Plume rise observations. The EPA database had concentration profiles at different distances downwind of various buildings. And so based on that research, next slide, what we did is we put in the source inputs for the different hours and cases that we had. We ran AERMOD for the different cases and got the predicted Plume rise values from the diagnostic file, and then compared predicted and observed Plume rise. We varied the entrainment constants. You can see the different cases we ran, case 1 through 5, varying alpha and beta. Alpha in the current model is 0.11. We found out that that actually worked the best, and it didn't really affect things much. We did change beta quite a bit and found that beta equal to 0.35 gave us the best performance with observations. So the next slide shows the results, kind of a typical result. We had quite a few results, but this kind of summarizes the results. You can see in the picture, Prime was under predicting the plume rise. And then when we put in the new entrainment constant, beta equal 0.35, we got higher plume rise and better agreement with observations. So from a theoretical point of view, beta equal to 0.35 is a better value, and it will give you better plume rise estimates. Next slide. So that was kind of the findings from this study. We should change beta to 0.35, keep alpha at 0.11, that's the current alpha. But now we need to run the valuation again to see how the models perform. So we just kind of repeated what we just talked about, the same databases, ran the databases, QQ plots, robust highest concentration, and but now we have additional model runs. So now you see the same P2, which is the PRIME2, like we evaluated before, but now we have what's called P2B, which is PRIME2 with that new entrainment constant. Then we have ORD. Now we have ORDB, which is the new beta. And now we have the current prime and prime with the new beta. So those are the different cases, the same databases, Bowline Point, Alaska North Slope, PRCI, same statistics. And then we'll kind of go through these. The plots get a little more hard to look at, let's say, with all of the points on there. But I think what we'll focus on is the table below. You can see PRIME2 actually got much better, 1.28, 1.08 for Bowline Point, and it ends up being the best performer now with the new beta, with the new entrainment constant. And ORD performs pretty good. I mean, it's almost the same as PRIME2B. So those two almost are about the same. Where Prime now is under predicting significantly with the enhanced plume rise. Next slide. This is kind of an important result here. You can see that PRIME2 now, with the enhanced plume rise, the overprediction now is only a factor of 1.5. Significant improvement. It's still overpredicting. And ORD, every model with the new beta shows lower concentrations because you have higher plume rise. And Prime still probably is the best overall predictor with or without the new beta. Okay, now we'll go through the monitors. Since the plume rise went up, with the new beta, all of the receptors that were under-predicting before are under-predicting even more. So we've got even more under-prediction. You can see with the new beta, models are under-predicting. We'll kind of go through these fairly quickly here. The next one, the second monitor, again, under-predicting significantly. And then monitor 3, again, under-predicting, but still PRIME2 beta is still looking pretty good. But now monitor 4, monitor 4, let's take a look at that one. You can see that PRIME2 and PRIME2 beta do pretty well still. I think the key is this next chart, which kind of summarizes the results. We have the current prime model we saw already, where PRIME2 is the best overall performer, as we talked about. Now with the new beta, we can see a little mixed agreement, but PRIME2 is still the overall best performer. Just it performs better at most of the receptors. And even though all of the predictions are under-predicted. Now, we were doing some analysis on this PRCI database, and we're finding that one of the reasons for the under-prediction is that the surface roughness input may be overestimated. It may be that the sigmas are way too high, and we're getting much more dispersion than we should because it's a much lower surface roughness. So we're going to be evaluating that and updating the inputs, and we think we're going to get much better agreement when we update some of the inputs to the model, which we have a lot better inputs. And so this is kind of a summary of PRIME2 and PRIME, like the best models. It looks like PRIME2 in the middle of the dark blue is kind of showing the overall best model. It's still the best based on what we're seeing overall. Now, PRIME2 with the beta is still almost just as good, but it's tending to underpredict significantly, but it's still doing better than PRIME overall doing better than PRIME. So, I mean, it's kind of leading to the conclusion that PRIME2 or PRIME2 with the new enhancements is the best model. And okay, yeah, we jumped to the first conclusion.
Sorry, so do you want to go back to this one?
No, we're going to hit that in a second here in the next bullet points, what I was saying. So let's go ahead. So the conclusion really is that the current PRIME model predicts the plume rise better when you change beta to 0.6 to 0.35. And with that improved plume rise, we see that the large overprediction for Alaska is decreased significantly. So that helps a lot. And we did get better agreement at Bowline Point, even decreasing the plume rise. Okay, the next conclusion is we see that with the current plume rise, PRIME2 provides the overall best agreement with field observations. With the improved plume rise, PRIME2 beta provides the best overall agreement. So what we really see is that PRIME2 and PRIME2B agree better with all field observations at the current AERMOD, and leads to the point where maybe the next release may have some new enhancements to improve predictions. And I'll turn it over to Sergio at this point.
Yeah, thank you, Ron. So what's next? Obviously, like I mentioned earlier, once you fix one thing in the model, you find that this model has to play with everything else that is in there. So there are more evaluations that will need to be done to evaluate why some models underpredict for the PRCI database. And like Ron mentioned, it seems like surface roughness may be one of the issues that might be causing that. We think that there'll be a more accurate model that will be available sometime in the near future. I mean, this is nice that we're having this collaboration with EPA, Office of Research and Development, and a lot of people actually. The APM committee has a lot of members that are providing their feedback and looking at some of this, and we have the same goal in mind. Whether it's EPA or the user community, we want to make sure that we have an accurate model. So I think we're on the right track on that. The other great news is that there's good funding from API or adequate funding at this point to do some additional research on PRIME2, and also to go through the process of submitting it for a peer-reviewed journal, right? This is part of the 5 steps of section 3.2.2 that will help us move these options from purely research options to beta options and eventually to default options. And as it comes to the entrainment constant, that will be an alpha option that will be in the next release. And at this point, EPA is thinking that it'll be sometime in early 2021. And by that time, we might even have perhaps a beta option that will have either like a single option or perhaps a combination of options that might be available. I know EPA is still working on that evaluation. And then the hope is that the alpha options that perform the best will go through the process of becoming beta options, and eventually they'll become default options as well. So as you are able, you know, like I guess I encourage all the people in this call that you can check some of these options, and if you find that they're performing well in certain cases and not so well in other cases, I mean, let us know. I think this is all good information that we can use. As Ron mentioned earlier, like the Alaska database seems to be one that is pretty unique in the case that AERMOD was almost calibrated to match it very well. But that's the one that doesn't seem to match the other ones. But now with these improvements on the Plume-Rice equations, the agreement seems to be much better for the PRIME2. So with that, I think, yeah, go ahead, Ron.
One point here that go back to your next slide.
Sure.
Yeah, I just wanted to mention that EPA is in the process of evaluating or taking like all of these options, and they're going to have, I think they said they have about 20 or 30 combinations of runs of different options, and they're going to run those against all these databases and see which combination provides the best agreement. So I'm thinking once they finish that, they might be the basis of the next official release. So they're in the process of doing that right now.
Right. Yeah, thanks. Yeah, that's a great great update on that. And that brings us to questions. So does anyone have any questions? Feel free, you can just unmute yourself and ask a question, or if you feel more comfortable, you can type it up in the chat box.
So Ron, Sergio, this is Howard Gebhardt.
Hi, Howard.
Hi, thanks for your presentation. As I was listening, it kind of occurred to me that what you're also finding is that the non-building downwash inputs like surface roughness and other things like that are kind of critical to getting the correct answer. So would you comment on the need then for users to maybe be more diligent about some of these other inputs in order to be sure that the what they get is a good answer out of the model?
Yeah, Howard, because we are looking at on this PRCI database kind of hourly cases, trying to find out why, comparing an hour prediction and observation, what's causing the difference. And what initially I found out is that they did measure sigma thetas, you know, during the experiment, but they actually didn't use those as input. And so when we actually used the actual sigma theta input, because the model was over predicting the spread of the plume and getting the low numbers, it actually improved the prediction. So that tells you getting better inputs. Now, if they would have had sigma V, that might also help. They didn't have that, but the sigma V is affected by the surface roughness. And so we evaluated that a little more and found out that we have the data to predict it on an hourly basis. And when we did that, we found out that the roughness was about a factor of 10 lower than what was input. So we haven't run that case yet, but we think that's going to really help change the sigmas and make the agreement even better. So it just tells you that getting really accurate inputs is going to help give you accurate numbers.
And I can add to that. I think you bring a great point, Howard. Even though we have the best, the most accurate theory right now for building downwash, that theory is inserted into the model, and that has to interact with the rest of it. So in that ecosystem, we're finding that there's some things that need to be corrected. And I mentioned that, you know, like Office of Research and Development saw that we were using the effective wind speed at the stack height. They didn't think that was a good option to have, you know. So then one of their options was actually using the average between the receptor height and the plume center line, you know, so which is consistent with the way that the rest of AERMOD works. So yeah, so as we're going through this process, we're uncovering other things that perhaps need adjustments, you know. But yeah, I think there's a lot of work still to be done, you know, and with the help of the user community, we can try to identify other priorities to kind of bring us closer to a more accurate model.
Well, I think it points out too, the PCR database, they had measurements at multiple levels. And so like on the wind speed, you know, you're going to get a profile that's more accurate out of AERMOD. So you're going to have a better wind speed input. So I think in general, people aren't willing to pay the money to maybe get these inputs, but I think it's going to give you more accurate answers, not always lower numbers, but it's going to give you more accurate information.
Yeah, thanks for the question, Howard. Anyone else has any other questions or comments? I'm kind of curious to know if anyone on the call has had a chance to use any of the alpha options for building downwash yet. And if you haven't, I guess we encourage you to try them out. And as Ron mentioned, you know, there's going to be at least one other option, you know, and some other alpha options related to non-downwash stuff as well.
Yeah, should mention that we have one person that has tried them and on some projects, and the PRIME2 in his case decreases concentrations significantly for wide, big structures, you know, very low buildings that are big, you know, 30 stacks on them. I mean, he's finding a factor of 3 or 4 reduction when he uses PRIME2, and tended to agree better with observations that he had around the facility. So he's kind of encouraged that the PRIME2 may help him out in the future on some of his permitting.
Well, thank you everybody for attending. One last chance for questions. Anybody else? Okay. Well, thanks again. Thanks, Sergio and Ron. It's greatly appreciated. It's always interesting to find out what else is going on. So this will be posted on our website eventually here. So let me know if you have any questions, and thanks again, everybody.
Yeah, thanks everyone.
Thank you guys. Great presentation.